Okay, now, the magnetic flux through a surface, and the surface we'll call S, is just phi sub b equals the surface integral of b dot n with respect to area. That is, the amount of b that actually penetrates the surface. Now, when I had the magnet in front of the coil, or the loop, okay, the field of the magnet was, well, if I'm facing you, the field of the magnet kind of comes out straight, but then it comes out like this, and it comes out like this. Okay, so when it hits the, how do I want to orient this? Let's say the magnet's here, okay, and the loop is here. Then straight away from the magnet, the field is perpendicular to the loop. Over here, it's a little bit in this direction. Go a little further, it's a little further in this direction. It's only the perpendicular component. If this was a fluid flow, the amount of fluid flowing across the surface is only going to be determined by the component of the velocity at any given point perpendicular to the surface. Could have said that a little more completely, but I think you know what I mean. Okay, and the unit of this is going to be units of B times units of area. Tesla times meter squared in SI units. Okay? Now, this is important because what you witnessed was the result of a changing flux creating a voltage, hence an electric field, or creating an electric field and hence a voltage. Okay? Whichever way you want to look at it. The rate of change of the flux with respect to time is equal to the EMF. Now this is EMF, not voltage. We use EMF usually when we're talking about induced fields, but it's a voltage, okay? It acts just like a voltage. Same effect that a voltage around that circuit would have if it was produced by a battery or some other source. Okay? So again, the rate of change with respect to time of the magnetic flux through a region is equal to the EMF around its boundary. Now, we remind you that that EMF is the amount of work per unit of charge around the boundary, which we're going to reinforce is the product of the charge and electric field and the distance around the boundary. Now, you don't necessarily have a uniform field around the boundary, so we'd have to say the average charge times the arc length of the boundary. Anyhow, we have this, okay? And what we're going to talk about right now is just circular boundaries, so everything's going to be nice and symmetric. So here we have now, in 3 dimensions, an X, Y, and a Z axis, we have a bad attempt to depict a circle in the XZ plane in green if you're not colorblind, but there's a circle, okay? It's a circular loop. We're going to say its radius is A, centered at the origin in the XZ plane. We have a magnetic field that I say is B naught equals negative B times J. Okay, so it's in this direction where B is a constant, so it's the same field throughout the loop, unlike the loop in the demonstration where the field was not uniform, but we'll just consider a uniform loop for right now. And if you don't have a uniform loop, if you know the formula for the, if you can derive the expression for the magnetic field, and then if you're lucky enough to be able to integrate it, you can find the flux anyway. Okay, but simple case, constant magnetic field, and the magnetic field's perpendicular to the loop, obviously, since the loop's in the XZ plane, and this is parallel to the J vector. Then the flux through this loop is the integral of the over the disk of B dot N dA. It's got to be B times pi A squared. Now that's a clockwise loop. Actually, it should be negative, because of course we said that was negative. Except with normal vector. The normal vector with respect to the orientation of the surface would be in this direction. So actually, I think I should have said that should be negative. You think that through? Okay? Then it doesn't really matter. You get the idea. Okay. Just keep your vectors careful and make sure you understand your orientations and do everything right. Well, now, that's simple enough. Okay, simple idea of flux is field times area. And pi a squared, of course, being the area of the circle. Okay, if B is changing, okay, I called this B naught. If that's your T equals 0 magnetic field, then your magnetic field, and I left off my J vector, okay, maybe your magnetic field is this. This is what would result from a rotating magnetic field sort of rotating at a constant angular velocity, constant rotational rate. And that angular velocity would be the omega. Okay? So we have B of t equals B, same B we had here, sine of omega t plus 3 pi over 2 seconds. Where t's in seconds, omega would then be in radians per second. Okay. Then we can write down the expression for the flux. And the flux is just what it was here, except, well, okay, we can, okay. I don't have room to really fix that. Phi b is going to be this times pi a squared, okay? So I kind of skipped that step and I wrote phi b, but it should be the derivative of phi b with respect to t. I did the derivative, then I wrote this down carelessly, I apologize. Okay? The rate of change of the flux is going to be this. Very easy, take the derivative. The SI units here are going to be Tesla meter squared per second, same as volts, and we've defined all these units. What is a Tesla? Okay. And you break all these units down to more fundamental units, and you can see that this is going to reduce down to volts, which is joules per coulomb or Newton meters per coulomb. So that, as it needs to be, the rate of change, time rate of change of your flux is an EMF. Okay, electromotive force in volts. Okay, now, I want to talk about current loops and dipoles, because one thing about magnetic fields is one of Gauss's laws, one of Maxwell's equations says that del dot B is 0. Magnetic field has no divergence. This is equivalent to saying there are no monopoles. Okay. Now we're going to consider a current loop, and then here we're going to consider an electric dipole. And what I want to point to is the fact that if this was a magnetic dipole, and I don't know what letter I'd use if it was a magnetic dipole, but you know, one magnetic charge and an opposite magnetic charge, we get the same form of the field due to this that we would get due to a loop of current. Okay? So I want to talk a little bit about the field created by the loop of current, and then we'll talk a little bit about the field created by an electric dipole, then draw the analogy, and then you can take that and run with it if you're so inclined, now or at any point in your life. Okay. Now, for this magnetic dipole, for this current loop, we can partition the loop, okay? And we can take a typical partition, typical interval of the partition, with a sample point. We're going to get an R vector toward the origin, and we got an I vector that's tangential. We'll do the I vector in white. Here's your I, here's your R sub I. They're drawn small. I don't know why I drew them that small, except I knew it didn't have much space. If you do your I delta S here, cross R, okay, you have this crossed into this, you get this. So at the origin, you've got a magnetic field that might look like this. Now, of course, your magnetic field is going to be the sum from all the intervals, but you can see if you use your right hand with any interval, the R vector always points toward the origin. The I vector is always in the counterclockwise tangential direction, and when you do the cross product, doesn't matter where you are, your thumb's going to be sticking straight up. So the sum of all these is just a vector that's straight up at this point. Okay. Now, if we move up to a point here, what's the field look like? Well, the way I've drawn this, it looks like this distance is about equal to the diameter of the circle, twice the radius. So this point is at least twice as far from any segment on the circle, any segment in your partition, as the origin. So when you sum up even the magnitudes of all the field contributions from these intervals of the partition, it's going to be at most 1/4, because of the inverse square nature of this thing, at most 1/4 the magnitude of this. Okay? But it's less than 1/4. And let's demonstrate why that is. It's because if we look at this thing from the side, where this little mark and this little mark indicate the extreme points of your loop, and we're looking at it in this direction, so we can't really see the loop. A point or a segment here, an R, if your ith segment is here in the direction into the board, your RI vector is going to be here. Okay? I thought I'd drawn a little arrow at the head of that vector, but I don't think I did. Okay? So your I cross RI, to cross I with RI, you're going to have to move your hand to this angle and cross it, and your thumb's going to be pointing in this direction, not this direction. And here's your contribution from the magnetic field. Okay? If we look at the opposite, the partition segment opposite this one, it's going to look a whole lot the same. That your B sub I is going to be here. Your delta B sub I prime is going to be here. These vectors are going to have equal and opposite components in the in a plane parallel to the XY plane, and you're going to be left with just well, you have the sum of the two Z components. Okay. okay, like so. Now, each of these vectors is on the order of a fourth as big as any of these vectors. When we add all these vectors here, the vector down here ends up much bigger than any of these, okay? Because we're adding vectors here that are basically on the order of less than a fourth as great as the vectors we added to get this one. And we're canceling out most of it because most of the component is in the plane parallel to the xy plane. The result is we get a very small field here. Falls up very rapidly. Now it's easy to write out the integrals, it's easy to write out the expressions and perform the integration to see just how this falls off. But it turns out it falls off about like the cube of your distance along the axis. Okay. Now with an electric dipole, what happens? Deciding how I want to color code this. I still don't know. Okay. If you consider this point is this far from the positive charge Q, 3 times as far from the negative charge. The result is that the vector you get from the positive charge, let's say that vector is this long, okay, and it's going to be in this direction because positive charges kind of repel the field. Don't want to go into too much detail about that. Okay, this is the vector we get from Q. So let's go ahead and make Q green so we can keep track of the fact that the green vector corresponds to the positive charge. The vector toward the negative charge, well, the negative charge sort of attracts the electric field. Haven't explained, Coulomb's law and so forth and the conventions, so I'm being a little vague about that, but it's pretty simple. Okay, this vector is only going to be a ninth as great because these are inverse square influences, so this vector is only going to be very small. So right here the field is pretty much just almost the same as the field due to the charge Q, the positive charge Q. So the resultant field is going to be just a little bit shorter than the field that would be there if negative Q wasn't. Now let's go down on the negative x-axis, partly because I don't have that much room up here. Didn't leave myself that much room. And let's, now I'm a little worried. Okay, I'm not sure I got all of this picture down here. It's a little hard to see on my screen, but I kind of think I got it. Okay, sorry for this distraction. Okay, now I want to move down here quite a ways. Okay, now I'm, how many of these units? 2, 3, 4, 5, 6 units away. That's probably too far. I just want to, I'm just going to move 2 units away from it. Now I want to move 3. 1, 2. I want to move to a point here. We'll consider this point a little bit later. Okay, so now this point is 3 times as far from negative Q as this point was from Q. This means, and I probably should have made these vectors bigger. I'm going to have to draw really short vectors here. This means that the field we get from negative Q is going to be represented by a vector is of the same length as this one. Okay? This is 3 units from here. This was 3 units from here. The vector I get from Q, okay, the vector that repels us from Q is going to be even shorter. So what I really need to do is make a little circle here and make the circle a lot bigger. This is just a magnified view of this. So now this vector has a length that you can actually see. Okay? Okay, well this is 3 units from here. So the magnitude of the field is 1/9 as great as it would be if you were 1 unit from here. Okay? It's 5 units from here, so the field is 1/25 as great as the magnitude of the field from one of these charges if you were just this far away. And a 25th is about 1/3 of a 9th. Okay, of course it's 9/25, which is a little less than 1/3. What color am I using? Okay. So we're going to have something like this. And we have a 9/25 ratio. Okay. Up here, the ratio of this to this was 1/4. Okay, well 1/4 is less than 9/25. And what I'm getting to is magnitude of the resultant is going to decrease the magnitude of this by more than this decreased the magnitude of this. Probably should have done that with more symbols, but okay, so that the resultant is going to be like so. Okay, and this is, length of this is 1 minus, not writing very well here, 1 minus of this, if that makes any sense. This vector is 1 minus one minus 1/24 of this one. Okay, so this is 75%. So this red vector is 75% of this one. This red vector is only about 70% of this one. We can write out the expressions and see that as we get far away, the field falls off as the cube, because, we'll do this again here, we'll take the picture we have here and make a bigger picture of our point. This, whatever it is, and what's my color? Green. And this I want to say bigger. I want to say, I could cross that word out, I'll erase it later. The ratio of these two lengths increases, and that decreases the magnitude of the resultant compared to either of these vectors. Now that's intuitive. It's easy to write out the expressions. Okay, if you're I don't know whether to use A or 2A for the separation of these things. I haven't looked at the conventions, and I haven't thought about the conventions in a while. Okay, so you've got a Q here and a negative Q here. When you're down here at position Y, your electric field is, and I'm going to write it out to see what the terms look like. It's just K Q squared over magnitude of Y plus A over 2 quantity squared minus KQ squared over the magnitude of Y minus A over 2 quantity squared. You simplify this expression, you'll get something that, as you move pretty far away, falls off as the Q, just like you do over here. Okay, so if you do the arithmetic of an electric dipole, well, the calculus of it, and the magnetic, or the current loop, you get the same form. And if this was some different letter than Q that represents two magnetic monopoles making up a magnetic dipole, then you would have the same behavior. If the Q's match up with the I and the radius of the loop and so forth. Don't want to derive the basic formulas that you use, but we want to get that concept. Because of this, there's no such thing as a monopole. Actually, it's not because of this. This expresses the fact that there's no such thing as a magnetic monopole. You can't take a positive magnetic charge and a negative magnetic charge because you can't isolate them. It's never been observed. Now, there's no mathematical or physical reason why it shouldn't be, but it's never been observed. So we kind of think maybe it's not possible, but we don't know why. I say we. People that really understand the field equations and so forth don't know why. I don't understand anything. Okay, compared to them. Okay, so that might be enough background now to start talking about Maxwell's equations.